Hello, algebra students. I'm with you here today to talk about logarithms and explore their special features and properties. We want to understand how we have certain properties of logarithms based on its definitions and how to apply those. Those will become especially important in applying the properties to solve certain exponential and logarithmic equations. So first off, some notes. Based on the definition of log, our last set of lectures, we used the definition of log, where we had log base a of x equals y is the same thing in exponential form as a to the y equals x. Okay, so this is how we rewrote something in log form to exponential and vice versa. Now, based on this definition, we have a few interesting features of logarithms. Number one, if we take the log of 0, what is that going to be equal to? Well, is that even possible? So if you think about this, this is like 10 to what power will give you 0. This is not possible. Okay. So we can never take the log of 0. There's no valid output, and that's or the log of a negative number is also not possible in the same sense, because you would say 10 to what power would equal some value that would be negative. That's not going to happen, not possible as well. So we have this domain restriction, which says that our argument, the inside of the log, must be greater than 0 and cannot be a negative or 0 in that word. So domain restriction is x cannot be 0 or negative. X must be greater than 0. I'll say that concisely in that one statement. And here we have that domain restrictions. Other sort of features that come into play. So if you have the log of 1, what will that equal to? Again, you want to remember that there's an understood 10. So you're pretty much saying 10 to what power will equal the value 1. Okay, so if you rewrote in exponential form, this would make sense. So 10 to what power will give you 1? Well, that has to be 0. So we have the log of 1 is always equal to 0, and hence the ln of 1 is also equal to 0 by the same reasoning. Ln, the only difference between our natural log and our log is our base. Natural log has a base e, so e to the 0 power equals 1. So these are two facts that are really good to know. And some other properties that come into play based on the definition. If you had log base a of a to the x, this will always equal the value x. So whenever your base, which is in your subscript, matches the base inside the actual logarithm, okay, to some exponent, then the entire expression on the left will just equal your exponent on the right. So that's a very good property that can be applied in certain situations and problems. Another property that you have that comes into play is a, by the same reasoning, a to the log a of x power, a to the log a base of x is all equal to x. Okay. So here we have matching bases, and what happens is when you have your base a matched with the base a of the logarithm and the exponent, you end up with the inside of the logarithm as your output. So here's another property we can apply. So all you have to try to do here is imagine just number values that take these place. This could be a 2, this could be a 3, this could be a 4, and it doesn't matter what it is, but whatever the exponent here is what your outcome will be, what it'll equal to. And the same reasoning goes to this special property. So note, these come up a lot, and you just want to be aware of, your domain restrictions and certain tricks in evaluating your logs. So now let's move on to our general properties of logs, which are very important in manipulating logarithmic expressions and equations, especially those that you want to solve. There's a lot of tricks. So first, just like we have our rules of exponents, we have certain properties based on those exponential rules for logarithms. Okay, so let's see. What we want to do is properties for logarithms can be applied in simplifying expressions and / equations. So first off, I'm going to say, since logs are inverse exponentials, they have certain properties that are built into them, just like we have exponential properties. So since logs are inverse exponentials, they have properties based on the exponential properties. So let's just go ahead and recall our rules for exponents. Okay, our rules for exponents. Number one, we had something called the product rule. And the product rule said that if you have two bases that are the same and you multiply them, you could add those two exponents. So here I have base x. If I multiply these two bases, I add my exponents to get x to the 5th power. Okay, that's called a product rule. Then we have our quotient rule. And our quotient rule is, if you have the same base and you divide, then it's the same thing as subtracting your exponents. So if I had, let's say, x to the 5th divided by x to the 3rd power, my bases are the same, so I could subtract my exponents and get x squared. The way I actually like to think about this one is that if you move the position of your base from numerator to denominator or denominator to numerator, you change the sign of the exponent. Okay, so I could bring this base up, it becomes a -3, and then I can add them. So the quotient rule is really the product rule said in a different way here. Okay, number 3, we had our product rule, quotient rule, we had our power rule. And our power rule was, if we had x squared cubed, you get x to the 6th power out of that. The power rule says that when you have a power to a power, you multiply these, and you get x to the 6th power. Okay, and that's how that one works. So the question you want to think about is, how do we express this? How is this applied to logs? Or how does this translate to log properties? Okay. So we have the analog for logs. So we're going to have a product rule for logs, a quotient rule, and a power rule. Okay, so let's go ahead and three main properties for logs. And when I say logs, I also mean the natural log under that umbrella. And the three main properties for logs or ln are the same thing. We have the product rule, we have the quotient rule, and three, we have the power rule. Am I writing this a little small here, or power rule? So let me go through all this one by one with you. Okay. And we'll see how we apply these. Okay, so number one, the product rule for logarithms. And what I do is I say, the rule is log base A of m times n. Okay, so usually the times is not apparent in the notation. It's just m and n beside each other, which of course implies multiplication. And I use m and m. There's other variables or letters used in other textbooks. Okay, this will always equal log base A of m plus log base A of n. So my number one rule is that if I have two items multiplied inside the logarithm in the argument, then I could separate them into addition units. Or, in the other way to think about it is, if I have two separate logarithms with the same base and they're being added, or in other words, there's a they're positive, then it's the same as combining them into one log and multiplying the insides of those logs. Okay, so this is how we would condense it or write as a single logarithm. We take these two logs and combine them into one log, or this is how we would expand a logarithm. Okay, that's our very first form here. And some things that you want to note is that m, the restriction is m and n must be, we know that these cannot be 0 or negative, so m and m must be greater than 0. Okay, so we're going to highlight this. And we'll do some quick examples. So illustration. Number one, how we apply this rule. Let's say I just have log base 3 of xy. Here I have a single logarithm with x times y inside the log, my argument. So I could separate this, expand this into two logs. I could say this is the same thing as saying log base 3 of x plus log base 3 of y. Okay. It goes like that. And let's say I had 2 ln of 4z. It works for natural logs as well. This is the same thing as saying ln, so remember there's an understood base e here, ln of 4 plus ln of z. So I could split it up into two natural logs. So that's how you apply the product rule. Now, typically in a problem you would have a combination of properties you have to apply. You might have to use the product rule and the power rule together. So we'll get to more of those complex examples after we go through all three properties. Okay, the next property is the quotient rule. Okay. And the quotient quotient rule, very similar. It's just subtraction. So number 2, we have the quotient rule or quotient property. And it goes like this: log base A of m over n is equivalent to log base A of the numerator. So numerator is m, denominator is n, so it will be the negative, or that's what we're going to subtract, log base A of n. These are equivalent expressions. And again, the restriction is where m and n must be greater than 0. So really important property here. And just to give you a little shortcut on how you could think about this, I always like to say if it's in the numerator, it's going to be positive. If it's in the denominator, it's going to be negative. Because sometimes you encounter problems where you have like 5 different terms in here, and you need to categorize them in different areas. So here's your denominator right there. So anything that's in the denominator, if you have more than one term, you can just add another log with a negative in front of it. And the same goes for the numerator. So some quick examples of how the quotient rule works. Number 1, we would say, let's see some of the examples I have over here. Number 1, if I had log base 3 of x over y. Okay. If I want to expand this logarithm by using my quotient rule, I would say this is the same thing as saying log base 3 of x minus log base 3 of y. Or, in other words, if I had 2 separate logs and I wanted to combine them, write them as a single log, I would recognize this has a negative, it goes in the denominator, this is a positive, this goes in the numerator, as long as these bases are the same. Really important idea. Okay, so there's one example. And then 2, if we had ln, let's say of 3, 4 divided by z in this case. This is equivalent to saying, oh, not ln of 3, sorry, just ln. ln has its own base, which is e. So this is e. Okay. So remember, there's an invisible e if it's not written there. This is equivalent to ln of 4 minus ln of z. And that's how you apply the quotient rule. So next up we have the power rule. And the power rule is what? Is if we have log base A of m, and I was just looking at what letters I use for the power. I'm just going to use P for power. Okay, that's the standard I use in my notes, but other people do it different ways, the books. So here I have some value or some variable that's placed to a certain exponent inside my logarithm. So remember, this is inside the logarithm. This is equivalent to saying the power up front times log base A of m. Okay, so this is the power rule for logarithms. This one could be a little tricky, but the idea is if you have a coefficient, it's the same as having that coefficient as an exponent inside the logarithm applied to your argument in the log. Okay, so some quick illustrations on that one, and then we'll do a few problems as a variety. to get you on your way to being able to solve some problems involving properties. So number one, let's go ahead and do, let's see. If I have log base 3 of x squared, how could I apply that power property? Or what do I know about the power property for logarithms to also express this in an alternative form? This will be equivalent to, since I only have one base inside the log, and that's applied to the second power, I'm going to bring that second power up front, so this becomes 2 log base 3 of x. So this is my equivalent form right here. So many times when we're trying to condense logs, we write this into the exponent, and then maybe sometimes we'll have to do some simplification inside the log, or sometimes it's easy to write the exponent out front and use it as a coefficient. It just depends on the problem. And two, if I had ln e to the third, this is a very useful property for the ln's of e's. This is the same thing as 3 ln of e. Now, since we're hitting this, little side note, what is ln of e equal to? I should have had that highlighted at the very beginning as well, but ln of e is always equal to 1. And why is that? Because ln of e has a base e, which equals 1, and e to the 1 equals e. So anyways, this is also equal to the value of 1. But if we were just purely rewriting what we have in its power form, we apply the power property to rewrite it this way, and you could see where the application is. This, and in this format, we could just think of this as 3 times 1 and get e value 3. I forgot to multiply by 3. So that's why it's always good to check your work there. Okay, so this part is equal to 1, but this whole thing is equal to value 3. And that's how you apply that power rule. Now, what we want to do is apply the properties. Let's do some examples and applications. Applications and / mixed examples. So the biggest ones, things we want to tackle is our main purpose, expand, or write as a single log, ln, if you can. Okay, so there's going to be 2 main things we want to do. You're going to want to expand these logarithms, or you're going to scrunch them together and combine them into a single log. And this is important. For problem solving. Okay, very important for problem solving. Okay, so anyways, let's see. Our first set of examples. So let's write as a sum or and or difference of of logs, or ln's, okay? Or basically we could say expand. And let's do some examples. Let's start with number 1. Let's say I had log base log of 2x squared over y. How can I expand all this out and apply my properties? So some steps to take here first is to check to see how many different logs can you form out of this, right, using your properties. If I'm wanting to expand this, I want to think about this and say, how many different logs can I make? So first off, my question is, how many different logs can I make from this? I could go and I could separate the 2, the x squared, and the y. So I could see that I'm going to make 3 different logs and use the properties. So notice that what I first want to tackle is applying the product and quotient rule. I also see a power in there, but I can wait to the very end. My very first goal is to separate the 3, right? So I can, here the answer is 3. 1, 2, 3. So I have a log I want for the 2, I want a separate log for the x squared, and I want a separate log for the y. And then I'll worry about the power rule at the end. So first, I want to use my power. I mean, after I just said it, my multiplication, my product and quotient rule. And then last, I want to do my power rule. Okay, so here, I'm going to take all this and write it up here. And make this into log. And the base that I want for each of these is whatever the base is right here. So there's an understood 10 right here. So this just becomes log understood base 10 of 2 plus the 2 is in the numerator, so it's a positive log. The x squared is in the numerator, so it's a positive, plus log x squared. And now my third one will be the y. It's in the denominator, so it'll be a negative, minus log of y. So there's my 3 logs. Next step is to see what else I could do to expand this or simplify. When I look at this term is good, this term is good, but this term could be expanded just a little bit further. And I could apply my power rule by putting the 2 out front. Log base 2 plus 2 log x plus 2 log of x minus log of y. So this would be my final expanded version of the first expression. So I'll say write as a sum or difference of logs or ln's, expand, and it might also say apply your power rule. It's usually assumed if you're expanding it to do all 3 of those. Okay, so that's my final answer in that case. Let's go ahead and do another one, or 2, 3. Let's say 2, the ln. I have ln of 4 square root of x. In this case, I want to again identify how many logs I'm going to do. Here I'm dealing with natural logs. So you have 2 ln's. I have an ln for my 4, and I have an ln for my square root of x. So I'm going to rewrite this as the ln of 4 plus the ln of the square root of x. Okay. Next step, I want to go ahead and apply any other power rules or do any other expanding that I need to. So here I notice I have a square root, and we know from our studies of roots and radicals that the square root is the same as to the 1/2 power, okay? Which, rewriting the statement, leads me to the expression ln of 4 plus, applying my power rule here, I have that exponent on my argument in my natural log, so that's equivalent to having the 1/2 out front, 1/2 ln x. Okay. And that would be my final answer. Now what I'm going to do is save more of these for writing as a single log. That's what we do most of our examples. So this next set of examples, we'll do the opposite. We're going to go from the expanded form, we're going to squish them together into a single log, if possible. So there's the restriction of having to have the same base that we always have to watch out for. Okay, so number one, next set, I think. So the next set of examples is write the following as a single logarithm, if possible. So again, you have to just be aware that it's not always possible to squish them all together in one log. So let's go ahead and start with number one. I have 2 log x plus log y. So the first really important thing to check when you're in the write as a single log mode, first check which bases are the same. To combine. Okay, we can only combine ones that have the same base. So if I look at this, I see that this is the same base as this, which are both understood tens, so we're good to go. Okay. So that's good. Now the other thing is, you're going to get some messy expressions with parentheses, lots of coefficients, and typically what we do here is we get rid of our coefficients first and apply the power rule and then combine them. It's the opposite of when we expanded. When we expanded, we apply the product and quotient rule and then the power rule. Here we want to do the power rule first. So second, what we want to do, if you have coefficients, you want to work with first. So sometimes you'll have a lot of parentheses in these expressions too, and you have to distribute your terms and do all the simplification first. So here what I'm going to do is I'm going to apply my power rule and rewrite this expression as log base 10 of x squared plus log of y. Okay. So now I have my 2 logarithms with the same base, and I can combine them. And the way I like to think of it is they're both positive, so they're both going to be multiplied in the numerator. So this becomes log parentheses. Use a lot of parentheses to keep your units together inside. Base 10 of x squared times y, and that will be my final answer. Okay. I also double check. Third, a good thing is to check. Is it all good? Are you as far as you've made it? Can you go any further? So one of the things that sometimes when you're learning math happens is you like to invent new steps and keep going. So there's wisdom in knowing where to stop, right? So the the saying goes, when the horse is dead, get off. So here, you want to stop right here. So this is log x squared times y. Nothing else we can do. So we stop there. Number 2, I'm going to step it up a little bit. What problems do I have here? All right, here's a good one. We'll have 2/1/2 log x minus log y plus log x minus 1. All right. In this case, I have 3 logs I want to squish down to 1 log. Now what I'm going to do is I'm going to add some bases there. Okay. So again, by the same guide we followed for this last example, we'll do that here, and I'll get rid of any coefficients if I have them. So I'm going to rewrite this as log base 3 x to the 1/2 power minus log base 3 of y plus log base 3 of x minus 1. Okay, so this is the only one that had a coefficient that I applied. Okay. What I want to do at this point is squish them together. So notice they all have the same base. So this base is the same as this base, is the same as this base. So I can put all of this together into a log base 3 parentheses, positive x to the 1/2 in the numerator, negative y in the denominator, positive x minus 1 in the numerator. There you go. And you could stop there, or we could say the equivalent is log base 3 of x to the 1/2 x minus 1 over y. This x to the 1/2 is the square root of x. So equivalently, I could write this as the square root of x. So either is acceptable, and what I want to do is check to make sure you can't simplify further. Sometimes what will happen is you might have the square root of x and x squared here, and you could use your rules of exponents to simplify. So always make sure this is as simple as possible, which it is. So this is good. So either answer is acceptable. Let's look at a third example on these types. If I had log base 3 of 7 minus log base 4 of x to the 3rd plus log base 4 of z. What I want to do here is notice that I have one base that's not the same as the others. Okay. So this is different than these two bases. So I can only combine these two, and this one just tags along. Log base 3 of 7 is a number value. It's going to be 3 to the first power is 3, 3 to the second power is 9, so it's going to be 1 point something to make that 7. So this is some number value that we could use your calculators to look up, but you've got to use your change of base. The rest here I could combine into, I'm going to say plus log base 4, these are both base 4. Now this is a negative, so this goes in the denominator as an x to the 3rd power. Okay, and this right here is z, so this could go in the numerator as a z. Now Now, also, what you might have noticed is I didn't put my 3 out in front of this log in this case, because if I did that, then I'd have to apply that same coefficient out front. So if I wanted to have a coefficient of 3, I'd have to change this coefficient as well. So in this case, it was advantageous not to apply my power rule and just keep the exponent as it is. Okay? So in this case, I didn't apply my power rule, and I just combined these two. So different problems require different methods, and that's where it gets tricky. You have to use your judgment. Usually when you're combining as one, you want to combine and then keep any exponents if you're going to simplify inside it later on. And this is as far as I could go with this, as far as combining into a single log. So here I just have a number value that tags along. Let's go ahead and try another one. And then we'll be done. We'll move on to how to apply these with solving. Okay, here's a good problem. Let's say I had ln of x minus 4 minus ln of x squared minus 2x minus 8. Okay. So in this case, we recognize that to combine these, we have to check to see the bases are the same, and they are. So this is an understood E base, this is an understood E base. So altogether this becomes ln x minus 4 over x squared minus 2x minus 8. Since I already have parentheses, I'll use square brackets. Okay, so based on my properties, positive numerator, negative denominator, and I've got that combined as 1. Now, am I done? Well, in a case like this, where you see that there's factors and polynomials involved, you want to look at reducing any of those if you can. So what I want to do is I want to get this in factored form and see if there's any way of reducing the inside of the log or simplifying it. Okay, this is x minus 4. What does this factor out to be? Here I have not very good numbers. So does this one factor? Well, we have a minus 8 plus 1, minus 4, and plus 2. So that looks like x minus 4. Yes, we do. X plus 2. So if I check this, minus 4x plus 2x, give me a minus 2x in the middle. Minus 4 times plus 2, give me minus 8. So actually the numbers are work. This works out really nicely. So what I end up with is an answer I can simplify internally in this case, and I'm left with ln of 1 over x plus 2. Okay. So that simplification of this original expression wasn't so apparent in its original way. You couldn't see that this whole thing would simplify to that until you've used your properties, applied your properties, and then you get something that's very simple as the outcome. Now note, there's another way you could write this as well. So you end up with 1 over x plus 2 in the denominator. So you could also write this as ln of x plus 2 to the negative 1 power, correct? Okay, because this is all in the denominator, so you could say this is all to the negative 1 power if I bring it up to the numerator. And then we could equivalently write this as negative ln of x plus 2. So there's 3 ways of saying the same thing here. Either answer would be acceptable on an exam or a quiz, etc. So be aware, sometimes when you're checking your work with textbook solutions for certain problems. It might be written this way, it might be written this way, it might be written this way. So it's very important to be fluent in writing your answer in several different formats based on what we know them to be equivalent to. Okay, that's it for today, and we'll continue. That's it for this piece for today, and we'll continue with how to apply these properties when we solve equations in a follow-up lecture. Thank you, and enjoy.